Hello everyone. Today we are going to discuss about Lagrange theorem and the geometrical meaning of it. So for that, let's first see what the Lagrange theorem actually states. It states that the general solution of linear partial differential equation Pp plus Qq equals R is given by this this phi of mu b equals 0, where this phi is an arbitrary function and u and v form a solution of equations of this equation where p, q, r are the functions of x, y, z. What does this mean? To understand the meaning of it, we first have to look to what the geometrical meaning of Lagrange's theorem is. So for the geometrical meaning, you have to understand that these equations give us different integral curves. These integral curves form this surface. Okay. Now we can, if you want to imagine it visually, then it can be considered as like this. So let's suppose we want to form a surface, a paraboloid, which looks like this. Okay. It's a three-dimensional surface, and if we have these equations of it, it means that these are the integral curves which we are going to find out by this relation or these equations, and this whole surface would be defined by this formula or this surface. Now we can think of this relation as g equals f of xy, which denotes surface. Because if we consider z to be r and function of p and q, then we know p and q are the partial derivatives of x and y. That means we can consider them as small changes with respect to x and small changes with respect to y. Okay, if I consider g component, then the small changes with respect to z would be accounted by this term here, del by del z. So you can think of it, the geometrical meaning of Lagrange's theorem is by thinking of as a surface is created, which is given by this equation, and the structures or the role of structures are played by the integral curves, which can be found out by using these equations. Now if you are still unclear about it, then let's see the proof of it so that it will be much easier for you to understand and to intuitively think about it. Okay, so let's see the proof. Proof of it describe the geometrical surface and how geometrically it can be visualized. So proof says that if we consider z equals f of xy as an integral surface, and we consider that the direction cosines are perpendicular to the integral surface p, and these are p q minus 1, then the equation this defines that the normal is perpendicular to the direction defined by direction ratio is this. That means the direction ratios p, q, r is tangential to the integral surface g equals f of xy. So if we move from any arbitrary point M on the surface in the direction PQR, we can trace out a unique integral curve of the equation dx by p, dy by q, and dz by r, such that the integral curve always lie on the surface. So what does that mean? To see all of this at once, let's again go through this proof. It says that we have a surface, okay? So this yellow is our surface, okay? This yellow is our surface, and we define a direction cosines for this surface. Direction cosines is always perpendicular to the direction, okay? Always perpendicular to the integral curve. So PQ minus 1 is the direction, defines the direction cosines normal to this integral curve, okay? Now, then the equation PQ plus QR equals QQ equals R defines that the normal is perpendicular to the direction. That means if we consider this equation, and this means this line here, this line defines the direction ratios PQR which are perpendicular to this normal, okay, in the surface. And if we consider any point on the surface M, and we go in the direction of PQR, since PQR is a direction which describes the surface, okay, it's a direction ratios of the surface which are perpendicular or on the or we can say which is tangential, yeah, that is the word. So these direction ratios are tangential on the surface. So you can imagine a surface, you can imagine a tangent, okay. Now at every single point of this curve it defines, so okay, you can think of it as, suppose you have a plane. So let's suppose we have a plane, yeah, so we have a plane, but as we have a surface, so this plane may be tilted a little bit like this way, okay. If that is the case, let's suppose we have this kind of, okay, maybe this kind of thing, okay, let's suppose we have this kind of surface. Then if we define direction ratios, so direction cosines which are defined by PQ minus 1, then they would point in this way. At every single point they would point outward of the surface, of this surface defined by g equals f of xy. Now we have the direction ratios which define the tangent of this surface. So always, so it will look like this. At this point the tangent look like this. The direction ratios would define this point. Similarly, this is how it changes. So let's suppose so that means that direction ratios are always tangential to the surface. That means they are always touching the surface. They are not going out of this surface like the direction ratios does, direction cosines does, okay. So if we define a point, or if we define a line or curve by tracing the points to which this direction ratios or tangents touch, then we can define a curve in this surface, okay. We can define a curve in this surface, and this curve is actually a solution of this equation. If that is the case, and if we have these direction ratios to be unique, then that means we have a unique curve for each point or for each direction. That means we can find out different curves. We can find out many curves defined by this equation. And these curves define the actual plane. So, which is defined by this equation, PP plus QQ plus R. So this is what the whole thing is, okay. This is how how geometrically you can understand it, okay. So we have a theorem for Lagrange's method for more than two independent variables. Let's take a look at it and let's try to solve some questions regarding it, okay. So just to see the theoretical part, it says that The theorem says that if we have any curve, any number of independent solutions of equation which looks like this. Now, if you compare this to the previous Lagrange's method of finding solution for two independent variables, we had u x y equals c1 and v x y to be c2. Now we had two independent variables, and that means we had two different variables, and we had, okay, we can say it in this way. So if we had previously two independent solutions of two independent variables of the equations which looks like, oh wait a second, what was it? It was dx by p, dy by q, dz by r, right? Yeah. So we had these equations, and then the relation of phi u v equals 0 had a general solution which looks like this. So actually, what is it saying is that we had this as our linear PDE. All right, we had this as a linear PDE, and we used these systems of equations to find out these solutions when we had only two independent variables x and y. But when we have a large number of n number of independent variables, then our PDE becomes this equation up to Pn, and we would have our system of equations which is given by these, and the solutions of these uh, system of equations is given by this. So that is the surface. This is the system of equations which gives us integral curves, and these are the actual integral curves if you see it geometrically. Okay, now let's see some questions so that it would be intuitive to us. So let's see a relatively easy question included in this kind of theorem, which is this. It was actually a past year question which was asked in BSc examination of mathematics 2078 in 2078. Okay, so it says that if u is a function of xyz which satisfy the PDE this, then so that u contains xyz only combinations uh, x plus y plus z and x square plus y square plus z square. So for solution we didn't do much. What we did is we found out the auxiliary equation, and we chose multipliers which satisfy this, which make this denominator 0, and I found out that 111 and xyz makes it 0. That means I get one curve defined by x plus y plus z, and another curve, actually it's a parabolic curve, which is x square plus y square plus z square. So which are exactly the things that were mentioned in the question. So this is how we prove it. So this is one of the questions involved with the theorem. Now let's see another topic.